Problem 1 from the 2009 exam is completely solvable until the very end. At the very end, we go into something about potential energy curves. We have not talked about that yet. I always save that until right before the AP exam, so I'll post some videos talking about potential energy curves in just a little bit. But first off, we have a mass of 3 kilograms. It's moving along the x-axis. It has some potential energy that is determined by where it is on the x-axis. And then they tell us that when the object passes through the point of negative 0.5, its velocity is 2 meters per second, okay? So I just went through and showed what the kinetic energy would be at exactly that point. Okay, so calculate the total mechanical energy of the object. Well, I know how much kinetic energy it has at that 0.5 meters, negative sign right there. I can figure out the kinetic energy at that point, and I get a kinetic energy of 6 joules right there. I'm then going to figure out what is the potential energy at negative 0.5, so I'm going to use this guy right here. 4 multiplied by 0.5, the quantity squared. Don't have to worry about the minus sign because it's squared. And I get a total energy there of 7 joules. 7 joules. Now, the next part says calculate the x-coordinate of any points on which the object has 0 kinetic energy. If the total energy is 7 joules and the kinetic energy is 0, then that means that it's all potential energy right now, so it has to have 7 joules of potential energy. So I'm going to have 7 is equal to 4x squared. I'm solving for x. We get the square root of 7 over 4, so plus or minus 1.3 meters. Those are the positions where we have 0 kinetic energy. Calculate the magnitude of the momentum of the object at 0.6 meters. I kind of did it a long way. I figured out what's the potential energy at 0.6 meters. I got 1.44 joules. I then subtracted that from the total energy to find the kinetic energy of 5.56 joules. Then I set that kinetic energy equal to 1/2 mv squared to figure out the velocity, 1.93 meters per second. And then I used the momentum is equal to mass times velocity to figure out the momentum at the 0.6 meters. So right now I have that the momentum is 5.78 kilogram meter per second. Let me pause right now to say, usually they will give full points if you include units. They're only going to ding you once if you miss units. You can't expect them to be dinging you constantly on problems. Usually at the end it'll say you got a point if you used correct units everywhere. We're going to pause right here dramatically. Okay, moving on to the other whiteboard. Now what they wanted us to do, calculate the magnitude of the acceleration of the object as it passes through 0.6 meters, okay? If you have a force versus displacement graph, so force on the y-axis, displacement on the x-axis, the area under that curve is going to be the energy. So if I take the derivative of the energy, I get the force. So what I'm doing here is I'm taking the derivative of the potential energy of 4x squared to figure out the force being applied to this object. I get 8x is equal to mass times acceleration. So I know what the mass of the object is. The mass of the object is 3. No, I'm okay. I looked at the wrong side. I flipped it. So 3 times a, the mass is 3. 8 multiplied by x, and I'm solving for the acceleration. I get an acceleration of 1.6 meters per second squared, okay? Again, remember, the area under the curve for a force versus position graph is the energy. So that means that you have to take the derivative of the energy to get the force. That's what I'm using there. Okay, the last part of the problem is the part that you need potential energy graphs for. It's asking us for the position as a function of time and the kinetic energy as a function of time. What we're going to find by going over potential energy graphs is that this object is basically bouncing back and forth between a position. So it's never escaping from this position. It's kind of going back and forth in a type of simple harmonic motion. And what that means is that the kinetic energy, which is always positive, it never dips below the x-axis. The kinetic energy is going from a maximum to 0, then back up to a maximum, then back down to 0, okay? We have not gone over potential energy curves. I will make some videos to go over that, but most of this problem was able to be completed without potential energy curves, and I will admit, straight off the bat, I hate potential energy curves. I think they are inherently stupid, so we will come to those. I will make some videos on that, but the rest of this problem was very approachable.